Okay, we're in Module D, Week 2, and what we're going to be dealing with this lab is column buckling. And what if we take a column, much like this one right here, and we're going to take a load, and we're going to know the end connections, and maybe we're going to have a pin-pin connection. We're going to talk about what that is. But just think about if we put a load, a compressive load on this surface right here and this surface, and we're going to compress that column. We know the cross-section of that is going to be 10 inches typical here and here, so it's a 10 by 10 inch column. It's a pretty good size column. And what we're going to do is put a load of 1500 kips on there, and we know this column is made of A36 steel. Now, what is A36 steel? A36 steel is a structural steel with a 36 KSI yield point. So if we go past that yield point, we're going to see this column potentially failing, permanent deformation. Okay. Want to think about that. Once you go past the yield point, you go into plastic deformation. Below the yield point, elastic deformation. You need to remember that. Now, we are going to ask, can this column carry this load? This is a typical textbook problem that we're going to do up to a certain point, and then the easy answer is we can check for compression. Well, we can come in here and say that compression is going to be force over area. So we take that compressive load of 1500 kips and we divide it by the area. So 10 by 10 inches, that's going to give us our area. And we know that the stress, because that stress is equal to force over area, is going to be 15 KSI. Now, the question you want to get in the habit of doing, is not just thinking textbook answers, but always answer, will this beam really hold up to this load? If I look at this thing, the allowable stress of A36 steel versus the internal stresses, I need to be able to hold more stress from the material than what I'm putting on it. And our material can hold 36 KSI. We're putting 15 KS on there, so it's going to hold. Okay, that's traditionally what we like to think about. But now we want to introduce a new concept, and you guys cover this in the theory courses. And the concept is elastic instability. Basically, when does a column not going to be rigid enough to hold its own shape under that load? Basically, it's going to buckle out of its plane. It's going to come out of plane. So it's not going to actually fail due to compression. It's actually going to pop out of plane, and then it's just going to bend and break. So no more unilateral loading being done here. So I've got this graph up here, and we want to talk about this graph. Basically, we have two formulas, two schools of thought here. There's actually three schools of thought. I put this graph on here so I could show the yield. If I was just doing a column and it definitely wasn't a long or a short column, it was just a short piece of material, then we could do the force over area, and that's going to work great, okay? But at some point, we're going to come out here and we're going to find that this column in this area is going to need to be considered a long or short column. And we have two formulas here. If it's in this area right here, okay, so a short column is going to use Johnson's formula. You need to remember that. A long column, so now we've got short, we've got longer columns, because we're going to define those here in a little bit, is going to be governed by an equation and a theory process called Euler's buckling theory. So it's not Euler, it's Euler's. Okay, so now we've got these three different things we're dealing with. Is it just a pure yield type failure, stress over, stress being force over area, or are we going to apply short theory using Johnson's, or are we going to do a long theory and use Euler's theory? Now, looking at this is for Johnson's formula curves. Materials are going to have different plots within these graphs. That relates to the modulus elasticity of the steels. Here we've got some 6061 T6 aluminum, which our elasticity for that in the English system is going to be around 10 to 11 mega psi. Our steels are going to be up around 30 mega psi. So we're going to see a different characteristic of steel versus aluminum. Okay, so the material is going to change how this column can react as well. Now what we have here is basically a concept of effective length. We can't just say a column is 8 feet long or 10 feet long or at some distance. We have to think about how are we holding this column from the ends. How are we doing this? And that's going to change what we consider the effective length of it. And so we need a K value, which is an end constant. Now on your lab sheet, you're going to have a graph that's going to have something talking, and it's basically a concept of end fixivity conditions here. And so we're going to come in here and put different K constants for different configurations. Now, pin is where it's going to move freely. It's not being held in there. If we're coming in here and using this fixed, we're actually holding the ends in grips. We're not letting it move and pivot about that point. Okay, so this may be a pivoted point we'll look at down here in a minute. This is fixed. Matter of fact, let's just go ahead and look at this down here. This is a common thing that we see out in industry where we have a beam, something welded here, welded to a frame, and if we were to put a compressive load on it, in one direction, it is pinned. Okay, so about the x-axis, it is a pinned connection. The deal is, in the y-axis, it is considered fixed because it can't freely rotate on there. So just because you see this kind of connection does not say that it is pinned in all axes. Okay, so we need to kind of watch out for that kind of stuff. The other thing is when we go from a pinned connection to a fixed, we're going to have that K value being 0.1 for the pin, 0.5 for the fixed. So just, you need to remember, fixing it is going to be half the length, effective length of the true length. So if I had a 10-foot column, it's going to be half as long. Now, what if we had a fixed end and a free end, and we just put a load on it and this thing can bend and move? Yes, now our effective length is going to be double because of the K constant is 2. Again, that goes into our K constant times the original length gives us our effective length. Now, what if we have a pinned versus a fixed connection? Then we're looking at probably a 0.7 effective length on there. I always like this little flow chart. First thing we're going to have to do is we're going to have to calculate our effective length, get our K constant, do our length on there. And then we have to calculate the radius of gyration. This is basically our moment of inertia, I. So if I had a rectangle prismatic shape, it would be base times height cubed over 12 if about the x-axis there. So we always like to see a larger I, a larger height being on that structure to give it a better property about the x-axis. The area, you guys know how to calculate that. Then we have what we call the slenderness ratio. Okay, that's going to be abbreviated by SR, and we would take the effective length divided by our radius of gyration. Then we have to figure our column constant. Once we get those values, we have SR and CR, we're coming to a shift where we have to make a decision. Is SR greater than the CR? If it is, then we're going to treat it like a long theory, and that's Euler's theory. Okay, in lab, you guys are going to be primarily dealing with Euler's theory. If it is not, if this is true, then it is going to be a short theory, and what we're going to have here is a Johnson's formula theory happening on here for short columns. So I put down here equations going Euler's theory. This is going to be in your lab manual, and this is going to be the equation that we're going to use here. Short theory would be this. So you guys aren't going to have to make these decisions in class for lab in this course because we're pretty much just going to be looking at long columns, which deals with Euler's. But again, we need to refresh and think about long, short, and yield type failures. Now, one of the things I want to point out here about Euler's theory is basically, and we're looking at the equation here, this is for long columns. You guys are going to go to lab and you're going to have this cool test fixture and you're going to mount it between different mounting methods, and then you're going to put a compressive load on it and you're going to have a dial gauge. Now, when you guys get the beams, do not try and bend the beams by yourself, because we've had students in the past, they just want to see how strong they are and they bend them and they put a permanent bend and now they are out of plane. We have them straightened out perfectly so that they'll be good for this test. And you want to put that indicator on there just where it makes contact. Now, it might bend the opposite direction of what you're measuring. If it does, then flip the gauge over and go to the other side. The TA will help you out with that. We're going to measure the critical load. And how does our critical load change with respect to maybe moment of area I value. If we look at that, the stronger the I value in a certain direction, then maybe it's going to bow one direction or the next. So you guys are going to have some shapes that are going to be rectangular or square, and you're going to be loading them, and you want to think, which direction is it going to come out of? Where's my I value going to be located at? So if it's 2 inches by quarter inch, it's probably going to come out of plane in the quarter inch thickness because I have a different I value for the two. Likewise, my column constant, depending on which direction it's going, the lower the column constant, then maybe I'm going to be able to hold my higher loads. Remember, that reflects all the way back up here to what we were talking about right here, a lower column constant. This is going to hold a higher load than this one will, because this one's going to tend to buckle quicker. So hopefully that helps you out. So other things you need to know for this lab is to be prepared and be upstairs on the 3rd floor in that little commons area to do this lab.